Okay, so good evening, everyone. Those who are on the Zoom as well as the other participants from the YouTube channel. Welcome back to the online interactive lecture series, which are being organized, as you know, by the India-based Neutrino Observatory for now 33 weeks to be precise, and this is the talk number 62, going to be given by Professor Vivek Datar. He's going to talk on electromagnetic radiation from the tiniest rotor 8 beryllium. That is the title of his topic. He's going to describe their work and the paper, the experiment connected with this topic. And just a minute or so of going over his brief profile. Dr. Vivek Datar was a senior professor at the Tata Institute of Fundamental Research in Mumbai from May 2015 to 20, and then project director, INO, India-based Neutrino Observatory since 2016 until he retired. And of course, before that, he was at BRC. We'll come to that. He obtained his PhD from University of Mumbai in 1983 and did postdoctoral work at IPN Orsay, France, and also Stony Brook, USA during 1986-88. Before moving, in fact, to TIFR, as I mentioned before, he was a distinguished scientist and head of the Nuclear Physics Division, NPD, in Baba Atomic Research Center, BRC, during 1975 to 2005. It's a long career at BRC. He was a senior professor of the Homi Bhabha National Institute, HBNI, and the Dean Academic for the Physical and Mathematical Sciences, BRC. He has also been an adjunct professor at the School of Natural Sciences, TIFR, that is before he joined the TIFR itself in 2015. And he joined NPD, BRC, as I mentioned, 2075, after a year at BRC school. And his areas of interest include low energy nuclear physics, tests of conservation laws and symmetries, and neutrino physics, of course. So with these few words on Professor Vivek Datar, I request him to deliver his lecture in this series today.
Okay. Thank you, Satya, for the introduction. So the topic of the talk today is electromagnetic radiation from the tiniest rotor that we know of, which is 8 beryllium. So 8 beryllium has just 8 nucleons, 4 protons and 4 neutrons. So the opening slide shows, a spinning top. Of course, maybe I should have put another slide before, another picture before that, which is the largest systems that we know of, which is rotating galaxies. Maybe I'll do that the next time I give this talk. So anyway, the spinning top is on a macroscopic scale. We have all played with these things when we were young, perhaps even a little when we were a little older, to see some of the nice things that spinning top can do, especially an asymmetric top. Then we have the hydrogen molecule, which of course exhibits a nice rotational spectrum. And in the nuclear case, we have the 8 beryllium nucleus, which consists of, which has a good overlap with the 2 alpha configuration, and which is as tiny as about 3.5 Fermi. So you can see this large difference in scales, length scales that are involved. Okay, now somehow, yeah. So this is the plan of my talk, a somewhat longish introduction. Then I move on to how do we know that this is spinning, how do we know that this is rotating. So this is by measuring the electromagnetic transitions in a particular set of states, 4 plus to the 2 plus. Then I will show some results and also summarize and say what are the future possibilities. Okay. We all know that electromagnetic signals are clean probes of any of the processes in atomic or nuclear or even particle systems. So you all probably have heard, of some of the very accurate things that have been both measured and predicted. Some numbers which are even going to 12 or 13 decimal places, like the magnetic moment of a electron or a muon, for instance, and they agree. So these are electromagnetic processes are probably the most well understood processes that we have in nature. However, in many of the cases in nuclei, they have to compete with the strong process, where the strong process cross section is very large as compared to the electromagnetic process. So you can say, in other words, that the branching of the electromagnetic decays, for instance, in case it is competing with a strong decay, or cross sections, you might say, if you are looking at a scattering process, or elastic or inelastic, then this is usually quite small. It's about a factor of at least 1,000, sometimes even more. Unless, of course, the strong process is inhibited. Then, of course, this becomes the process, the main process. But where it has to compete with the strong process, this is usually small. Coming to beryllium-8, it's an unstable nucleus in the ground state. It has a lifetime of about 10 to the power of minus 16 seconds. And therefore, you might say that the complementary thing to that would be that its width is very narrow. It's of the order of a few electron volts. Because it is unstable with such a short half-life, you cannot scatter electrons of it. Otherwise, these are usually very nice things that can be done on stable nuclei. You can get charge density distributions, and this is not possible in the case of beryllium-8 because it's so short-lived. However, you can look at another electromagnetic process, namely the gamma ray decay from excited states, which in this case, because the ground state itself is a resonance, a narrow resonance, albeit, the excited states become broader resonances. However, you could look for gamma decay from there, although the experiment might be very challenging. So this is a partial level scheme of the beryllium-8 nucleus. The ground state has a width of about a few electron volts. I think this number has to be updated. Somehow I didn't do that. It's about 5.6 electrons. That's there in the next slide. Then you have the 2+ state, which is actually again a resonance at 3 MeV or so, which has a width of about 1.5 MeV, quite broad. And then there is the 4+ resonance, which is at 11.4 MeV, which is about 3.5 MeV width. Notice that the ground state of beryllium-8, which is, as I said, having a width, so very small width, can decay into 2 alphas. So it is about 92 keV only above the threshold for alpha-alpha. Okay, so I'll admit somebody has just joined. Okay, so what is its importance? It's extremely important in nuclear astrophysics because you have a set of reactions in the so-called PP chain, PP1, PP2, PP3 chains, which produce nuclei up to about boron-8. But then boron-8 beta decays into beryllium-8, and then that quickly decays into 2 alpha particles. So it's very difficult to cross this bridge and to have a capture reaction on beryllium-8 to form heavier nuclei. So in 1939, Bethe proposed that there is a 3 alpha reaction that produces carbon-12, and then carbon-12 is of course stable. Then you can capture protons and alphas and so on, and you can make heavier nuclei. And so you can use the fusion reaction to go all the way up to even iron. This process was actually used to calculate whether this can be done. However, it was quickly realized by Hoyle, Opic, and later by some calculations of saltpeter that you need to first of all produce beryllium-8, and that lives on the time scale of strong interactions for a very long time. The typical time scale of strong processes is about 10 to the minus 23 seconds, and 10 to the minus 16 seconds lifetime of beryllium-8 is a pretty long time scale. So during that time, if an alpha gets captured, then you can produce carbon-12. And this was worked out by Hoyle, as I said, Opic, and saltpeter. But the last and the best calculation of saltpeter showed that even that is not enough to produce carbon-12 in the quantities required. So that is when Hoyle came up with this brilliant idea that not only have you to produce beryllium-8 resonantly, but you have to also produce carbon-12 resonantly. So there has to be a resonance at a slightly higher energy than the alpha plus beryllium-8 threshold and it has to be roughly at about 7.6 MeV. And basically Hoyle went and told the experimenters that you better look for it, because otherwise you can't produce carbon-12. And very quickly, this was found by Dunbar et al. In the same year, actually, that Hoyle predicted this. So these are pictures of Bethe, who is the father of nuclear astrophysics, and Fred Hoyle. The other thing that I would like to say is that alpha clusters are in a way special to nuclei. In fact, the first nuclear model was an alpha cluster model. Uh, so why is that so? Why is alpha cluster special? The alpha particle is special because it has a large binding energy. So 28 MeV binding energy. So the binding energy per nucleon is 7 MeV, which is close to the saturation binding energy of a nucleon in a nucleus, which is about 8.5 MeV or so. So this 7 MeV is already very close to that. Also, it is very hard to excite the alpha. The first excited state is at about 20 MeV. So it's a sort of rigid, unit. Among the alpha cluster states that have been predicted, and this was done by Ikeda in the 60s, so-called alpha linear chain states and so on. Beryllium-8 happens to be the simplest because this is just 2 alpha particles. Then he had predicted, chain nuclei consisting of 3, 4 alpha particles in a linear configuration. So carbon-12, oxygen-16, and so on, all the way up to calcium-40. He had predicted these states, and they occur just above the certain energies and so on. But beryllium-8 is obviously the simplest of these chain states. The energy and the decay width of this beryllium-8 is, of course, determined by the strong interaction, and its large width, which almost exhausts the so-called Wigner sum rule for decay into alpha-alpha, that certainly indicates that this is of an alpha-alpha structure. However, quite often it has happened that although the widths and so on might agree, but the structure, when probed with electromagnetic probes, doesn't quite show that kind of behavior. And so you have to put in certain other ingredients as well. And so the electromagnetic transitions actually provide a very stringent test of the structure, both through electromagnetic transitions, through other electromagnetic measurements like the charge distributions, magnetic moments, transition magnetic moments, and so on. Okay, so before I go into how would we test or how would we try to measure observables related to beryllium-8, let me just point out the importance of beryllium-8 also in a completely different area. Namely, it provides a way of looking at particles that might tell us something about possibly dark matter, possibly new interactions, and so on. So this is a particle which is in the news in recent times, in the last 4 or 5 years or so, the so-called X17. It's supposed to be a particle which has a rest mass of about 17 MeV, and it is believed that such a particle exists through experiments which have looked for its decay into E plus E minus channel. And how have they looked for it? They have looked for it through the lithium 7p resonant reaction, which populates a certain state in beryllium-8. And what is shown here is the excited states of beryllium-8. So apart from the 3 states that I just showed you in an earlier slide, there are states like 17.64, which is a 1 plus. So 1 plus refers to the angular momentum and the parity of that state, and T refers to the isospin. So the state at 17.64 is a 1 plus state and a T equal to 1 state. Similarly, there is another state at 18.15, which is also 1 plus, but it has 0 isospin. So it's a so-called spin 0. And then this group that claimed to have measured this or have found evidence for this particle actually looked for decays from both of these resonances, the 18.15 and the 17.64. They didn't see any evidence for this particle in the decay of the 17.64, but they did find evidence in the decay of the 18.15 state. Later on, they even looked at the helium-4 excited states. So there is a resonant state at 21 MeV or so, which is a 0 minus state. These are not very often found in even nuclei. But this was a nice case which they could look at. So they looked at the 0 minus to 0 plus decay, and they found evidence for this, which was in corroboration with their earlier results in beryllium 8. What was the result? They looked for it in the. I will go through this very quickly. This is a PhysRev letter paper published in 2016, and then they have another paper in the EPG European Physics Journal Web of Conferences in 2020, where they report the helium-4 search, and they find corroborating evidence in either case. Basically, the idea is that you populate a particular resonance using a suitable energy of proton, and then look for E plus E minus decay, a very rare branch that they are looking at. But if you look at, for instance, here, lithium 7p, and the final channel is E plus E minus, and beryllium 8 in the ground state, then you find that there is at certain angles, because if this X decays into E plus E minus, if it is at rest, of course, these two should come out at 180 degrees. But if it is moving, then the E plus E minus comes out in the lab at an angle which is slightly smaller than 180 degrees. So, for instance, you can see that there is a bump here at about 140 degrees in this reaction at both 1.04 and 1.1 MeV, and not there if you go beyond the resonance at 1.2 on the higher side and 0.8 on the lower side. So there's no bump here and here, but you see a tiny bump here. And so they can reconstruct the invariant mass. And I hope you can see that, because I put in many figures. Maybe I should have reduced the number of figures in this. But there is a peak in the invariant mass spectrum at about 17 MeV or so. Okay, so in this case, is at 16.66, but there is an error bar of about 0.2 MeV anyway. So if they take a mean between the latest results from beryllium 8 and helium 4, they find that, of course, the branching is very small. The width or the partial width for decay of those excited states into this X17, this hypothetical new particle, is of the order of -5 or -6 electron volts only. And this is a exclusion plot which is shown. So there are other experiments which have tried to look for this, have not found it. At CERN, for instance, there is an experiment which looked for through Bremsstrahlung to try to produce this particle and then look for its decay. This is published in 2018 in a PhysRev letter paper, and they have ruled out most of the phase space that is possible, but there is a small zone where this particle could still exist. And so there have to be obviously other experiments to either rule it out or confirm it. Okay, now we come back to beryllium 8. So how do we know that these resonances exist? One way of looking at that is through alpha-alpha scattering. So if there is a resonance, then the alpha-alphas, if you look at the phase shift in this elastic scattering, it should undergo a 180-degree phase shift or a change of phase shift by about 180 degrees. And this is shown in the delta 0 channel, where it goes through about a 180-degree phase shift. In the L equal to 2 channel, it does not quite show that, but a 120-degree shift. And similarly, in the L equal to 4 channel, it shows a change of about 140 degrees. These are the data. This is actually taken from a very standard text in nuclear physics by 2 Nobel laureates, Bohr and Mortensen. This is the second volume. So they give this as an example of rotor, the lightest rotor. That's how we, in fact, got into this experiment. Okay. The radiative capture cross-section in various partial waves was actually calculated by Langanke and Rolfs, and they showed that at about 11 MeV or so in the center of mass of the alpha-alpha system, you should see a cross-section for this radiative capture peaking at about 100 plus barns, about 134 nanobarns actually. If you calculate, and they calculated the BE2 for this, the so-called reduced electromagnetic transition probability for the type of electric transition with multipolarity 2, then this comes out to be about 20 times what you expect from a so-called single particle estimate. This Weisskopf unit is calculated in terms of just single particle transitions. And if there is any enhancement above that, then you say that there is collectivity. And in this case, there are only 4 protons. So if it is to be enhanced, you can expect an enhancement of about 16 times if all of the protons cooperate. But of course, you can also have deformation, so that can also lead to an additional, increase, enhancement of the BE2. And so, if you were to, for instance, what they computed in these 2 papers is that the BE2 should be about 20 times single particle estimate. So it's called so-called in Weisskopf unit, because Weisskopf first estimated this in the 50s. But for the 2+ to 0+ transition, this should be even more enhanced. It should be even 4 times of this. That means 75 Weisskopf unit. Now, you might say that 20, 75, I mean, how do we get a feel for what is the enhancement? So the thing to do would be to compare it to the so-called static quadrupole moment. This is what leads to enhancement, collective enhancement. And that is proportional to z squared r to the power of 4. So r to the power of 4 is proportional to a to the power of 4/3. So if you scale this BE2 by that, then you should put everybody on an equal footing. So if you look at the so-called super deformed states in rare earth nuclei, and these have been found in the mid 80s in Daresbury. The first case was 152 dysprosium. So if you scale that large BE2, they found about 1,000 times Weisskopf unit. But of course, Z is also much larger. So if you scale that with the Z squared a to the 4/3 factor, you get a number like 0.11. If you do that for beryllium-8, for the 4+ to 2+, it comes out to be 0.08, not very far from here. So it has a similar kind of enhancements. But for the 2+ to 0+, it's even larger. It's about 3 times that, 0.3. However, in spite of all of this enhancement, the gamma branch, as compared to the strong decay into 2 alpha particles, is just 10 to the -7. You can see this also from here. The elastic cross section is of the order of barns, whereas this is only about 100 nanobarns. So this, you can get an order of magnitude estimate right there. So it's a difficult measurement to do. In nuclear physics, typically we do measurements of the order of 10 to the -4, 10 to the -5 branch usually. This is somewhat smaller than that. So, okay. What are the calculations telling us? So apart from this relatively simplistic calculations using the alpha cluster model, which Rawls and Langanke did in the mid 80s, there were more sophisticated methods, in fact, initiated by an Indian who was in TIFR in the beginning. Then he went to the US, but I think did his PhD with Hans Bethe, and then went to Illinois. So he started these kind of ab initio calculations, as they're called. And as of now, the state of art is in 2020 that you can go with these ab initio calculations up to about A equal to 13 or A equal to 14. Of course, you can also use other approximation techniques to go even to heavier nuclei. But the real hard ab initio calculations using the 2-body potential and the 3-body potentials using the Green's function technique can go up to about A equal to 13 or A equal to 14. And so this is one such calculation done in 2000 by this group of Viringa, Piper, Carlson, Putter, the Illinois and Argonne National Lab group, where they have computed the ground state and excited states of beryllium-8. So these are the very early calculations using the variational Monte Carlo, and using that as a starting point for the so-called Green's function Monte Carlo, in which they propagate better and better wave functions you get as you go along in time, and they can lead you to the lowest states for both for the ground and excited states. And this is the comparison between experiment and theory. It's not terribly great, but it's reasonably good. And the differences are doing better than the absolute energies themselves. So the absolute energies are also not doing too bad. They're off by about 2 MeV or so.
Vivek, is it Pandari Pandey? Is it Pandari Pandey?
Yes, sure. Yeah, it's the same Pandari Pandey.
You did not mention the name.
No, I mentioned Pandari Pandey. No, I mentioned that he was, in fact, he was earlier in TIFR, then went with Bethe to do his PhD, and then went to Illinois.
You mentioned that,
he started this series of ab initio calculations for nuclei. Okay. So now coming to the electromagnetic transitions itself, if you want to measure it, Then we, of course, we first tried a measurement using only, measurement of the 2 decay alphas. I'll come to the technique that we used here, but the idea being that you shoot a alpha beam onto a gas target, which is confined in a gas cell, and then look for you don't see the gamma ray from the 4+ to 2+ transition, but you look at the 2 alphas that come out following this gamma ray transition after the 2+ resonance decays into 2 alphas. Now, the idea here is that when such a thing happens, the 2 alphas come out at an angle which is less than 90 degrees. If you shoot an alpha and it elastically scatters off another alpha, then the angle between these two in the lab is 90 degrees. Of course, in the center of mass, it is 180 degrees, but in the lab, it is the relative angle comes out to be 90 degrees. On the other hand, if some energy is taken away by the gamma ray, then this so-called folding angle, instead of being 90 degrees, becomes something like 60 degrees for the 4+ to 2+. So we tried to use that technique, but it turned out that the backgrounds levels of nitrogen in the gas are too much, and you cannot do that measurement by just looking at the alpha particles. So then we had to measure the gamma rays as well. And so then finally, it turns out that you have to measure the alphas as well as the gamma. So you have to look at all the 3 bodies in the final state. So we did that in a first measurement. We did that to about 35% precision. I will show you some of the results from there. However, these don't quite agree with the initial ab initio calculations. And we said that, okay, a more accurate measurement of that is needed. So a measurement at least at the 10% level, if not better. So let me first say what the schematic of the method that we used is. So we shoot an alpha beam on a helium-4 gas target. Normally in nuclear physics experiments, the bulk of experiments actually use solid targets. So we have a thin foil, either self-supporting foil, or it has a backing which is stronger, and therefore you have very thin targets evaporated and so on, or electroplated onto a backing. But basically they are solid targets. However, this required the use of a gas target. So that itself has its complications. I'll come to that a little later. So you do that, and then you measure the gamma ray transition. So this is the gamma ray which you measure using gamma ray detectors of as high an efficiency as you can. And then you measure the 2 alphas at this folding angle. In this case, it turns out that the folding angle is of the order of 60 degrees. If you go above the resonance energy, it becomes somewhat different from there, or below the resonance, it becomes somewhat different. So you have to have a range of angles that you're going to measure. So basically, you measure the 2 alphas and the gamma, and the sum of it, some of these energies should add up to the beam energy. Okay, but you should see a bump in the gamma ray spectrum at about 8 MeV, and similarly a bump in the sum energy of the alphas. Okay, so before I come to that, I should just show you where this was done. This was done in the Pelletron-Linac facility at TIFR Mumbai. So this is a joint project with the very close collaboration between the Bhabha Atomic Research Center and the Tata Institute of Fundamental Research. Of course, they are sister organizations in the Department of Atomic Energy. And this is a very nice picture of the building, the Pelletron building. So it houses this vertical machine, 14 MV tandem. So you get negative ions coming in, they get selected, go into the accelerator, which is itself in a SF6 environment, because that is a good insulating gas. Then at the high voltage terminal, you strip ions of all the electrons that you can, and then it gets accelerated by the positive terminal voltage, comes down somewhere here, and then gets bent by an analyzing magnet into a beam line here. So this is the so-called old beam hall, which was the old cascade generator hall. And then you do experiments here. Later on, in 2002, half of it, and then the full complement of superconducting Linac booster modules came up in 2007. And one of the modules is shown opened up here. It's basically a copper resonator, and then that is coated with lead. Lead goes superconducting when it is lowered to a temperature of helium. In fact, it happens even earlier than that. And then there are 4 of these modules per cryo module. and then 7 such. So you get 28 of these, gaps, cavities, and you can roughly double the energy which you can get with the 14 MV tandem accelerator. So you can go up to, for instance, about 250 MeV or so silicon ions. Of course, in this experiment, we used only the pelletron. We didn't use the superconducting booster. The apparatus that we used in the first experiment, which was the first measurement of this 4 plus to 2 plus gamma ray branch, consisted of a gas target chamber. So you had a chamber which was sealed off from the entry side and the exit side, so the accelerator side and the beam dump side, by Kapton foils, which are kept here. Sorry, this is the Kapton foil, is shown here with this arrow here, and similarly a Kapton foil on this side. So both on the entry and exit, we had these Kapton foils, which enabled you to put 1 atmosphere of helium in this whole chamber and have 10 to the power minus 6 millibar, both on the accelerator side as well as the beam dump side. So the Kapton foil is, of course, strong enough to maintain this pressure differential, but more importantly, it can also undergo radiation damage and keep its integrity intact for the whole time that we did this experiment. So, for instance, roughly 10 days of beam time we had, and we really didn't need to change the foil. Of course, in one instance, we did change the foil, but just for precautionary purposes when we went to the lowest beam energy. So, because the alpha particles are going through this foil all the time, even if you have about a nanoampere or 2 particle nanoampere of alpha beam going through this, if you take a typical mylar or polypropylene film, which is about a micron thick, that will get enough radiation damage that it will break up in about 50 to 100 times smaller time than a Kapton foil. So Kapton foil is very radiation resistant, radiation damage resistant. Okay, and then we put detectors to detect the alpha particles. So this is a front view of those detectors. We initially used pin diodes, silicon pin diodes, about 500 micron thick and 9 millimeter by 9 millimeter square. And they were arranged like this. This was Suresh Kumar's idea of packing them like this. And also, he contributed, by the way, crucially, to prevent background from this region to reach the silicon pin diodes by putting a very simple baffle here, or a limiter, you might say. So this is just a piece of metal foil with a hole here, so that only things happening in this region, those alphas can reach the pin diodes, and things happening from the, let's say, the Kapton foil, which is a 1 milligram per square centimeter, is a very thick target as compared to the gas, that does not reach the detectors. Okay, so this way you isolate what you see to a region of about a centimeter or a little more than a centimeter around this limiting aperture. Okay, so this is as far as the alpha particles go. Then you put BGO detectors. BGO is something called bismuth germanate. It has a high density of about 7 or so, and it has also a high Z because it contains bismuth. The average Z is high, so you can get a photo peak efficiency which is rather high, and so the overall photo peak efficiency of these two detectors put in close proximity to this is about 25% or so. Okay, so you can see the detectors, the gamma ray detectors here above, and then there is another 7 set of detectors here, and the beam comes in from here and goes away on the other side. And after doing all the data analysis, so this is a picture of, by the way, of the chamber when it is opened up. So you can see the pin diodes here, you can see the entry pipe and then the exit pipe. And of course, this is opened up, so you don't see the gamma ray detectors here. And there is also a possibility of putting solid foils. When you want to, for instance, calibrate the particle and gamma ray detectors with standard, with alpha particles of known energy and gamma rays of known energy. So if you put, for instance, carbon foil, then you can excite inelastically with the alpha beam the 4.44 MeV state in carbon 12. So you can see the gamma ray in coincidence with the alphas. Similarly, if you put mylar, then that also has oxygen in it. And so that way you can excite states in oxygen 16. So the 6.13 MeV state you can excite. That way you can make sure that the calibrations are done. So we used to do that periodically, maybe every day or every half a day or something like that. So if you once we analyzed all that data, these are 2D spectra of the gamma ray energy versus the alpha sum energy. Then this is a spectrum of that on the resonance, and this is off the resonance. So of course, you can see a blob here, which is not present here. But of course, there is also a huge amount of background. Okay, so you have to pull out this small signal from this big background. So by putting suitable two-dimensional gates, one can do that. And so on resonance, you see some energy peak of about 20.5 MeV or so. So that is because, of course, the alpha particles lose energy as they come in, but also the decay alphas lose energy as they go towards the detectors, because there is also gas in between. And so the sum energy actually occurs at a slightly smaller energy. But this is the kind of signal that we have. And if you go up in energy, where you would expect the background to be dominant, and you're also off resonance. So you see that this is a more or less slight increasing background, which you see, but there is no evidence of a peak. So using this data, we could say that we could conclude that the radiative capture cross-section on resonance is about 165 nanobarn, but with a large error bar, about a 33 to 35% error bar. And off resonance, it is about 40 nanobarn, but with a large error also. And this is to be compared with the alpha cluster model calculation of these cross sections. If you compute a BE2 in a very simplistic way, namely you put a Bright-Wigner resonance, which of course it doesn't look like. If you remember the profile of the capture cross section, it doesn't really look like a Bright-Wigner. But this is the simplistic way in which we analyzed it, then you can extract a BE2, and that turns out to be about 25 in some units, E squared Fermi 4. Could be compared with the alpha cluster model, which is about 22. And the Viringa 2000 calculation, which was 18.2, but later Viringa did a better calculation using the Green's function Monte Carlo, and he came up with this, a better computation, came up with this number, and he said, oh, this agrees beautifully with this result that you have. But of course, remember that the error bar is 35%. So the fact that it agrees is not really as attractive as it sounded to Viringa. So anyway, this was the paper published. This was a private communication, so we gave him credit, but he was not a co-author. So then we asked him to actually do this little better, and he became part of the next set of experiments that we did, the second following experiment. Okay. So how could we improve on this result? Reduce that error bar from about 35% to about 10%. So of course, the experiment I already told you, it was carried out. But this time, instead of just 2 energies, we aimed at actually measuring 5 energies. But finally, because of various issues with the accelerator ion source and the ion source at the top, the RF ion source and the charge exchange, we could do 4 energies. But still, that was a major improvement over the previous one. Of course, this gas target was similar to the one that we used. The alpha particles were detected not in an array of 6 silicon pin diodes, but now we had a much better detector, an annular silicon strip detector. So it had theta readout on one side and phi readout on the other. So the efficiency for detecting the alphas improved considerably as a result of this. And so these were the dimensions. For the gamma rays as well, we used 19 detectors instead of 7 on top and bottom. So we had a complement of 38 hexagonal close-packed bismuth germanium detectors versus the 14 that we used earlier. The major improvement was actually the heavy metal shield that we used around the Kapton window. So in the earlier case, we had just put some stainless steel block. They didn't do a good job of blocking the gamma rays from alpha scattering elastically on the Kapton foils. But with the heavy metal shield, we could do it much better. And this led to the VGO detectors being actually very cool. They were not seeing the 4.4 MeV from the alpha Kapton interaction. And then, of course, a slightly modified aperture was designed to shield the scattered beam. So we also designed a new chamber and so on, in which this was done. This experiment was done. And so this is a schematic of the new setup. And this is the heavy metal shield that I was telling you about. And this is the annular silicon strip detector, double-sided strip detector. So it had theta readout on one side. Actually, it was a quad detector, but we shorted 2 parts of the quad in order to reduce the number of electronic channels. So a quad on the left side and 2 quads on the right side were shorted. And then they went, each of these theta and phi channels went to their respective preamplifiers, timing discriminators, and TDCs, and so on. So I'm not showing that here, a schematic of that. But anyway, whatever parameters had to be measured, namely the energies and the times, they were basically measured using this detector. And similarly, the energies and times of the 38 BGO detectors were also measured. This is a cross-section, as you would see it from the bottom of the top detector shield, and as you would see it from the top of this array of 19 detectors. This is very close packed and so on. They had good efficiency. And so this was the place where you could either put a foil target for calibration purposes, as I said, or an aperture. So when the target was pulled out, the aperture basically came in the way and prevented alpha particles from this region to reach the detector. So only a 1 or 2 centimeter region from here actually reached the, sorry, I'm doing it the other way around. The alpha beam comes in from here, and only from this region they reach the silicon strip detector. Okay, so these are pictures of the apparatus. I'm not doing probably too well in time, so I should speed up a little bit. These are the BGO detectors. These are the silicon detectors from the back side and front side. This is the apparatus as seen when you open up the top foil, because flange. So there's the bottom flange here which stays, and this is the foil arrangement where you can actually see the beam on alumina. Then there is a limiter somewhere here, and then carbon and mylar foils can be mounted to the calibration. Okay, so these are some spectra just to show that the apparatus works. So these are some alpha calibration spectra with the mylar, which contains carbon and oxygen at a certain energy, and just one ring. But this sort of calibration is there for all the 16 rings and also the 5 segments. Similarly, this is a time spectrum. This is showing a coincidence time spectrum with about 10 nanosecond full width and half maximum between one of the BGOs and the silicon strip detector. And finally, when you take all this data and put it all together, do put all the cuts that you need to put in terms of time on the BGO silicon strip detector between the 2 silicon strip detector channels themselves. So you look for opposing areas of the silicon strip detector where these alphas should come out. So the phi should be different by about 180 degrees. And the theta, of course, can be between some region and some region. And so we put the right cuts and get this 2-dimensional spectrum. E gamma versus E sum, where E sum here refers to the sum of the silicon strip detector energies. So you can see a much cleaner band here. Of course, the gamma ray response at high energies is such that you get a tail on the lower side. So that is also evident here. But there is this little background here, considerable background, which we had thought would not be there and which would have led to a much nicer picture. But as happens in many experiments, Murphy's law operates, and the things that you don't expect to happen indeed do happen. So something was, we thought, simplified in the plumbing of the gas manifold, but that last minute change was not helium leak checked, and that probably led to this small leak of nitrogen, which has led to this kind of background. Nevertheless, the data is pretty clean as it stands. And these are just some alpha plus gamma ray sum energies. So all 3 particles summed up in energy at off the resonance and on the resonance. Okay? And so you can convert these to cross sections, provided you can do a Monte Carlo simulation of this experiment. And so this was Monte Carlo simulation was done using all these things: extended gas target, taking into account energy loss, angular distribution of the gamma rays, decay alphas, gamma ray response using Xian. And then, of course, you generate a 2D spectrum. As we saw there, experimental spectrum. You can also simulate a spectrum, then put the gates that you actually want to put, and then extract cross sections at these 4 beam energies. And then these are just some finer details. I think I'll skip these in order to keep in time and also leave some time for questions. So these are just Monte Carlo simulations to show our the distance from the silicon strip detector from the center was about 70 mm. So this is where it was, and so there these are the efficiency in percentage times the effective target thickness in terms of millimeter. Effectively, the target thickness, as I will show in the next slide, was about between 10 and 15 millimeters. So then this efficiency amounts to about this is in terms of millimeters, right? So this is in terms of, sorry, percentage. Okay, here for instance, this is like about if you take 15 millimeters, then there's about 70% or so for the alpha detection efficiency. Okay. So these are the plots of the efficiency, the effective target thickness for various alpha energies. So you can see that for the lowest energy, this goes on behind the aperture. So the folding angle, sorry, for the higher energies, it goes to back. So the folding angle has decreased. And for the higher energies, it goes up. And so anyway, these are the simulations that were used in extracting the radiative capture cross sections. So finally, when you extract the radiative capture cross section at these 4 beam energies, what is shown in red is the old data, the 2005 data. You can see the large error bars. We had it only at 2 energies, on the resonance and off the resonance. At in the subsequent experiment, we had these 4 beam energies, and so these are lower than the beam energy on the resonance, slightly higher, and then much higher. Of course, this is only an upper bound. We can't extract a finite number there. So the cross section is below about 20 nanobars. And okay, before I leave that, I should also show you the so-called cluster model theory. So that is this line here. So this is the theory, and this agrees reasonably well with that, except at this energy point. And if you do a Bright-Wigner fit, then this is the dashed so-called best fit that we could get. And again, as I said, this is a simplistic approach. We just fit a Bright-Wigner shape and then extract a BE2 from there. You extract a partial width and then a BE2. Okay, so these are some Green's function calculations of Wieringa and Pastor, which they did for this experiment. And they suggest that you stop between 0.08 to 0.12. They evolve the approximate wave function in time, in imaginary time. That's the so-called Green's function Monte Carlo method. They take a trial wave function and evolve it in imaginary time. And they say that between this, so the star shows where they would like to stop. And this is where they evaluate all the energies, the charge radii, and the quadrupole moments, then the BE2, and so on. So the cluster model gives this number, the experiment gives this number, and the ab initio calculation, which they did at that time, gives this number. Okay. So this doesn't compare terribly well with the experimental result that we had at the time. But as I said, the caveat is that we are fitting a Bright-Wigner, which is not necessarily the best way of analyzing this data. I mean, the cross sections are okay, but in trying to get a radiative width, we might be approaching it too simplistically. But anyway, that's what we did for the purposes of the paper, and extracted a partial radiative width. And as I said, this agrees a little better with the cluster model, which we know should not be the best approach. Nevertheless, what we pointed out in that paper was that you need basically to take into account also the reaction mechanism. So the gamma ray can be emitted before the collision and also after the collision, and these two amplitudes actually should be added to the amplitude when it has formed the resonance and then decays. So these two amplitudes should be added. So-called external and internal Bremsstrahlung contribution should be added. And so that is not done in the case of the GFMC calculation. And so perhaps when that is done, the agreement will be better. That is what we were saying at that time. Also, if you were to go to the 2+ to 0+, which we have not measured in this measurement, of course, but were you to do that, then the difference between the cluster model and the ab initio model is even starker. It's different by a factor of 2. Cluster model gives 40, and this gives 20 in some units, E squared for V4 units. So this was the second PRL that we had on this set of measurements. Subsequently, the Saha Institute group of Subinit Roy, so he had a PhD student, Suprita Chakrabarti, who did this much better analysis of this data. So the data is from the same experiment, but R matrix analysis was done. Actually, this was pointed out in a seminar that I gave in Argonne National Lab. John Schiffer pointed out that, why don't you do a R matrix analysis? Of course, we didn't have the programs and wherewithal to do that. Subsequently, I talked to Subinit. He said that he could do it. He had a PhD student also who would be willing to do it. And so this was done using the R matrix code and so on. And so this, you can see, is also very better fit of the data than we did with the Bright-Wigner. And not only that, they also fit all the elastic scattering excitation functions. So for instance, they fitted the elastic scattering at various angles. The data is from here. And these references are actually given in the text of Bohr and Mortensen. And so the phase shift data was also fit using this R matrix analysis, and they do pretty well. So the partial width that was extracted was about 9 milli-electron volts. That leads to a BE2 of about 28.4 E squared Fermi 4, which is in much better agreement with 27.2. So one possibility is that the external Bremsstrahlung amplitudes are small. That's a possibility, certainly. Or that if we take them into account in a calculation, let's say ab initio plus external and internal Bremsstrahlung, that might give you a number which is different. Then that might agree with this. So we don't know. That kind of analysis. Viringa had said that he would give it a try because he had done such a similar thing for the N plus helium-4 case. But this case would be much harder. So he said he would give it a try. Okay. So I summarize this. So we have a measurement of the 4+ to 2+ transition to about 10% accuracy. And this I have already said, that a better theory combining ab initio with reaction models is needed. The R matrix analysis, of course, gives a better number for the partial gamma ray width. But a more challenging measurement of this 2+ to 0+, which in spite of the larger enhancement in the cluster model, of course, in the ab initio, it is not that much enhanced. Although it is enhanced as compared to the Weisskopf unit, it's about 35 units of that. But the branching here, because the gamma ray energy is much lower, it's about at least a 50-fold smaller cross section that we have, and so this would be a more challenging measurement. And so I have some possibilities here mentioned here. There is one possibility, of course, of measuring this through the boron 11 p alpha channel, which populates the 2+ state at as low an energy as 163 kV. So the resonance is at a very low energy. You just need an ion source on a 200 kV deck to do that. But there are challenging things there as well. The random count rate is extremely large. So you would have to have extremely fast alpha detectors as well as gamma ray detectors. It's not impossible, but probably a more amenable way would be, and perhaps even a cleaner way would be, to use a gas target. Now, of course, it is not possible to use a gas target of the sort that we used for this experiment, where the energy was much higher. The beam energy was 22 MeV, whereas here you would require a 6 MeV energy on resonance. Okay, so at that energy, you would have to change these foils, Kapton foils during the experiment. Not only that, the alpha particle also will lose energy in the on the way before it goes to that zone that you are actually looking at. And finally, the 2 alpha particles that come out also would lose energy in the gas. They are lower energy, so they would lose a lot of energy. So the best way we think of doing this experiment is to actually do it with a gas jet target. So that's what is mentioned here. So you shoot an alpha beam on a gas jet target. You look at the 2 alphas. The gas jet target essentially is a 2 millimeter by 2 millimeter cross section target. And people have built, in fact, gas jets which provide target thicknesses comparable to solid targets. And we have a brand new accelerator at Saha Institute where you can actually span the resonance energy from 3 to 9 MeV. And since you're using a helium gas jet, which is pure, you can ensure that it is pure and so on, then the experiment is in general cleaner. Of course, you would still need segmented detectors for particles as well as for gamma ray. But these are things that we have, at least in the country. The other challenge of this experiment is that the folding angle of these two alpha particles that come out subsequent to decay is very small. It's only 20 degrees. So you have to contend with a large elastic background count rate and therefore a large, random count rate. But again, these are things that, in my view, can be tackled. A more interesting thing that could be done if once you develop a gas jet target, a so-called supersonic gas jet target, and these, as I said, have been developed elsewhere. We need only about 100th target thickness of those state-of-art targets, gas jet target that have been developed. If you can develop that, then you can also look at other things. If you were to sit on the resonance plus half of the width, that means you come in with a beam energy, which is resonance energy plus the width, half of the width, then you can try to look for so-called intrastate E2 transitions, which means from one edge of the resonance to the other edge of the resonance. So you go from E of the E resonance energy of the 4 plus to, you start out with this energy plus gamma by 2, you land up with E resonance minus gamma by 2. And there again, the branching ratio is about 100 times less than what we measured here. It's difficult, but not unthinkable. And the same gas jet target could be used. Of course, the accelerator would have to be different because you have to start out with the energy, which is about 25, 26 MeV. But fortunately, next door to Saha Institute is the Variable Energy Cyclotron Center, where you can provide these kind of beam energies. 20 MeV beams are perfectly possible. 20 to 30 MeV is what we require, and they're exactly in the on the table at DECC. So you just have to move your gas jet target from Saha Institute to about 50 meters away in the experimental beam hall at the Variable Energy Cyclotron Center at Kolkata. So you could look for this. Now, why is it interesting to do that? One of the interests is, of course, that you would measure the so-called diagonal E2 moment. What we measured in this experiment was the transition E2 moment. So from 4 plus to 2 plus. Whereas here we would be measuring, since you are in the same resonance, you would be measuring the diagonal E2 moment, essentially, quote unquote. So you would measure a quadrupole moment of a state as short-lived as 10 to the minus 22, 23 seconds. Okay? This is something that is quite attractive. Also, as far as I know, there is no observation of an intra-resonance electromagnetic transition in either an atomic system or in a hadronic system. I would be happy to be proven wrong, but as far as I could search, for instance, the closest is the so-called delta resonance, which is a resonance in the pion-nucleon system. If you shoot a pion of about the right energy of about 170 MeV or so, then on a nucleon, proton or neutron, then you can excite this so-called delta resonance, the 3/2 J pi equal to 3/2 plus resonance, and isospin also 3/2 resonance, which has a very large width, about 117 MeV. So people have, of course, seen the delta to nucleon decay through M1 photon. Okay, and that branch has been seen. The gamma by total width is of the order of 610 to the minus 3. That has been observed. But the intra-resonance branch from one edge of the resonance to the other edge of the same resonance, that has not been seen. It should be about 15 times or so weaker than this. But as far as I know, it has not been seen. So this is interesting from that point of view as well. And of course, such a method of electromagnetic decay from unbound states can be useful for studying electromagnetic decays in other particle unbound states like 5 lithium, 6 beryllium, and they can give us information about these very short-lived and momentarily excited states. Okay, so these are just some pictures which I will just run through of the gas jet target development that is going on in Kolkata. It's a Saha Institute BECC collaboration. They first simulated this using some simulation software called Consol, this gas jet, and then also fabricated components. You see, so the gas is fed in from here at several bar, and then it expands in vacuum, and then gets picked up by this this gadget here, and then gets pumped out. by so-called roots pumps, which can handle very large volumes of gas. So the idea is that you have a certain density of atoms per square centimeter here, which you would like to have, let's say 10 to the power of 17 atoms of helium per square centimeter in a 2 millimeter or 3 millimeter by 3 millimeter, tubular structure here. And then the rest of the zone, you have essentially vacuum. So so this is a windowless, gas jet target. And so you have to have pumps, roots pumps on either side, and also pumps here to recirculate and maybe purify this helium-4 gas. So the same gas is, taken in, compressed, purified, and then again passed here. And this is also useful for other experiments which require gas jet targets. So these are experiments of astrophysical interest and so on. So that is why they chose to try to build this apparatus. And perhaps if this gets built, we might see the 2+ to 0+ measurement as well as possibly the intra-resonance measurement in future. Of course, done by a younger set of people. So I should acknowledge, of course, the team that made these experiments possible. My colleagues in BRC, Deepak Chakravarti, Suresh Kumar, who is, of course, attending this talk, Shiva Behra, Ambar Chatterjee, Mirgule, Mitra, Ramchandran Raut, Prakash Raut, Aradhana Srivastav, colleagues from TIFR, Vandana Nanal and Raj Pillai, colleague from IUAC Delhi, P. Sugathan, then theory people, Pastor Viringa from Argonne. And at that time, there was also an experimenter who was interested in it, Lister. And then 2 colleagues from the UK who came in from York University. And then, of course, the final thing that I showed, starting the development of the gas jet target and the R matrix analysis that was done by Subinit and Suprita. Of course, we have to, in all these experiments, unless the Pelletron LINAC facility operates, which is due to the staff, these experiments will not run. So this is the final slide, and thank you.
Thank you. Thank you very much, Professor Datar, for a very nice, very, I would say, giving such a nice overview of the physics behind, but also so beautifully explained the experimental techniques and also, of course, some of the future directions in this possible measurements in future and opportunities. So it's very, very nice, even for, I would say, non-experts. And I hope there are some questions. So those who are on the Zoom, please ask your questions directly. You can just unmute yourself and ask question to the speaker. By the time I want to take one question from the YouTube by a participant by name Abhinav Chaudhary. The question is, do anomalies in the radioactive decay of beryllium-8 point to the existence of a new force of nature?
So you are referring to the one of the initial slides that I showed, right?
That's right, I think.
Let me see. Yeah, this so-called X70 particle. Now there is this is one group in Hungary which has claimed the existence of this particle through the search for its possible decay into E plus E minus in these 2 reactions. No other group has yet confirmed this. In fact, the CERN group did not find evidence to support it, but of course they have not ruled it out completely, because in the parameter space that I showed you in the next slide, there is still some room for its existence. But there are also other groups who are trying to repeat these experiments with with a different set of apparatus. And there was a group in Australia that has recently measured a very tiny branch relevant to the formation and decay of the Hoyle state. So they have made a beautiful measurement, which I just came to know recently. It's in a PRL published not a few months ago. So the spokesperson for that experiment said, I in fact asked him this question in some web conference that took place recently, and he said that yes, they are looking into the possibility of repeating the experiment, because they have a solenoidal electron positron spectrometer, because they were actually detecting the E plus E minus decay of the 7.65 MeV state in carbon. So they said we'll look into the possibility of trying to increase the currents in that so as to bend these higher energy E plus and E minus. And then the rest of the, stuff they have particle detectors. So they can certainly look into that. And, but as I said, this is actually quite a, this is quite a carefully done experiment, but unless this is repeated, we won't know whether this is right. And if it is right, of course, then this would be a great thing because, there are already people who are trying to analyze it and they say, yeah, there should be a fifth force and so on. But I think, theorists can certainly interpret this and in terms of new interactions and so on. But I think the task right now is to actually show that this experimental result is correct. And that is, I think, the main thing, which will take some time. I think it will take maybe 2-3 years time to show, unless somebody comes up with a brilliant idea of using some existing setup. Yeah. Does that answer your question?
Sir.
Acha, he's on YouTube, so we cannot use feedback.
Okay. Let me also take another question. I'm not sure Rajaji has a question or not. But of course, you can ask. By the time, let me take one question from Dhruv Mulmule. Have we also tried the P plus Li, P plus lithium, proton plus lithium, similar to alpha for the same study as the earlier paper shown? Also, is the search for X11, where you are, I think, just before, planned in future at any Indian facility?
As far as I know, there is no group in India which is trying to look for it. It basically boils down to having a detector set up for measuring the E plus and E minus and also their momenta. So measuring momenta means that you should have a set of detectors before. Suppose you use, for instance, plastic phosphate detectors to measure the energies and to make sure also that they are electrons, because they can be particles, protons, and so on also. So you use normally in these cases phosphate detectors. So there are two layers to it: a thin detector and a thick detector, and they are looked at by the same photomultiplier. So the thin detector stops protons, alphas, and so on. And so if you have a measurement in the thin detector as well as in the thick detector, a much larger signal in the thick detector, then you can conclude that from this delta EE combination that it's an electron-like event. But you also need to measure its momentum, because after all you want to measure the invariant mass. So the invariant mass involves measurement of the energy as well as its momentum. Momentum is a vector quantity, so you require to know where exactly it hit the detector. So usually people use detectors which have position resolutions of the order of a few millimeters at least in front of these electron-positron detectors. Okay, so they are usually gas detectors or maybe silicon detectors, strip detectors, and so on. So that kind of a setup has to be there, and we don't have any such setup in the country. I did talk to a colleague in TIFR to try to find out whether we can borrow something from Stony Brook. In fact, he had done a postdoctoral, and many of us have also done postdocs there. So we probably should be able to borrow that apparatus which is lying unused there. But it has not yet happened. The other question was, can you populate the 11 MeV resonance using this P proton-induced reaction on lithium 7, right? That would, that's probably not the best way of populating this resonance. Also, if I remember right, the threshold is at something like 17 MeV or so, 16, 17 MeV. Let me see. Sorry, I should terminate this. Yeah. So if you were to come in with the lithium plus P, you would come somewhere here. So you are far away from this. So you would require a gamma decay. So this is also not possible. So if lithium plus P were somewhere here, then with a small proton energy, you could have populated this. But that is not the case. So if you land up somewhere here, those things decay by alphas. they will not even populate the resonance that you want to populate. So alpha alpha is the best way of populating the 4+ resonance. Okay.
Okay. Right, sir. No questions from here. So, are there any questions from Zoom for Professor Datar? Yeah. Deepak, you want to
Yeah,
ask?
Deepak has a question. He has raised his hand.
Yes, there's a question. I mean, you said that the Bright-Wigner shape is not the appropriate shape to fit. Why is
Yeah,
that?
that's right. That's right. Bright-Wigner is not. See, Bright-Wigner was proposed in the days of the, the neutron capture or neutron resonances, which were seen. So they are very sharp resonances. So they, stick out like a sore thumb on a background. So very strong and narrow resonances is what these Bright-Wigner resonances were used to describe. Now here you have a very broad resonance. I mean, 3.5 MeV is the same order of magnitude as 11.4 MeV, right? So probably this is not the best way of describing. I mean, this is not. I shouldn't say probably. This is not the best way of describing it. And R matrix analysis is probably the way. There you take into account interference between background and the resonant amplitude and so on. And so that is the way to go. And that is certainly a more sophisticated analysis.
So this should be also reflected in the gamma energy spectrum.
No. What you're saying is that the line shape.
Yes, yes.
Yeah, the line shape in principle should be. They have not computed this for the R matrix. And also, I should say that our line shape with using the BGO detectors that we used are not so fantastic that you can, if a particular line shape is predicted, that we would be able to see it in experiment is not clear. I don't think we will be able to see it either, because these are not very high resolution detectors. Okay.
Okay.
So for that, you would have to use something like the lanthanum bromide detectors, which have about typically. So the BGO detector, by the way, has typically resolutions of the order of 10 to 12% by root E, E in MeV. Okay. Whereas lanthanum bromide is about 3 to 4 times better resolution, about 3% by root E, where E is in MeV. So at 1 MeV, it's 3%. So that is one possibility. The other possibility is that you can use large high purity germanium detectors, which are surrounded by BGO. Usually that is used in the anti-Compton shield, but you can also use it in the add-back mode. And as was shown several years ago, if you use that in the add-back mode, then that has a much better line shape as compared to, let's say, high energy gamma ray detectors, even sodium iodide. For instance, sodium iodide has typically 7% by root E. So this is even better than that. And that is another possibility. But again, it depends on what you are trying to measure, and whether, if this is something that you want to measure with accuracy, then of course you should use those detectors. Lanthanum bromide, incidentally, we have a few of them, but you can't pack them in the way that we have done. You certainly can't find 14 lanthanum bromides, and certainly not in hexagonal configuration. But okay, you can make do with, if you had 14 of them, you could certainly use them. Yeah, I don't know whether that answers your question, Deepak.
Yes. Thank you. Thank you.
Yeah. So Suresh Kumar has a question.
Okay.
Yeah, Suresh, please unmute and ask your question.
Oh, Vivek,
Yes.
you told about lanthanum bromide.
Yes.
So I just wanted to know what is the status of our Paris collaboration for the lanthanum bromide array.
So I think they had one kind of sort of dry run in, I don't remember where it was. Probably it was in IPN Orsay or somewhere, where they put together, I think, about a dozen or so of such detectors. And I don't know what is the status with that, but I think it was a reasonably successful run. So they used phosphate detectors there, for people who don't know about this Paris collaboration. So there is a collaboration which is going to contribute detectors and then use them in radiative capture or giant dipole resonance studies, looking at high energy photons in collisions of radioactive ion beams with stable nuclei. So the first which consists of cesium iodide and then backed by lanthanum bromide. So such detectors have been commercially built, and so I think there are a couple of them with at TIFR. We had also proposed to buy 2 of them. I don't think that has gone through probably, or maybe we have by now. I don't know. And then several of them are there in other European labs. So they put all these things together in a sort of dry run, and I think that was reasonably successful. Of course, you have to have a radioactive ion beam facility. So the one in Ganil is what was targeted. But in principle, this detector array could also go to any other radioactive ion beam facility. For instance, Isolde, high Isolde, or it could go to Riken. Of course, provided you are able to defend the beam time for that.
Sudhiranjan is also collaborating in this.
Sudhiranjan was also part of this Paris collaboration.
I don't know whether
he retired. I don't know whether he's still there in that. But there would be a younger set of people from VCC. That's true. Maybe even from Science should. Of course, in TIFR, I think there are two or three people in that collaboration. 2, I think.
Yeah, Vandana
and Indranil, I think, are there.
Prakash Raut is also, I think.
Prakash is also there from BRC, yes. And maybe 1 or 2 more, I don't know. In recent days.
It was a nice talk. Thank you.
Okay, thank you. Thank you.
Okay, sir. Are there any more questions, please? If not, let us thank Professor Datar for really a nice talk, and also for bringing up this nice discussion. All of you who have asked these nice questions to kind of bring out some more details and interesting information. So with that, we come to the end of this lecture today. But before I close the meeting, I want to announce that the next talk on 14th December, the next day, we are going to have another equally interesting talk titled as Extraterrestrial Life, the Most Elusive Customer. This is going to be given by Professor Sujan Sen Gupta from Indian Institute of Astrophysics, Bengaluru. So once again, all of you are welcome to this interesting lecture next Monday on 6 p.m. So with that, let me thank the speaker as well as all the participants, and see you next week at 6 p.m.
Thank you.